started. We're going to get started today. Welcome everybody to our annual heavy lecture series, and I welcome you to our first lecture for the 2010 season. It's my pleasure to introduce to you my friend and colleague, Karl Kaiser, who's our first speaker this year. I just want to give you a little bit of background on Karl for those of you that don't know Karl. He came here to Canada in 1971 from Austria with his wife Sylvia, and shortly thereafter started his connection to Brock University because Karl actually received his chemistry degree here from the Department of Chemistry right here at Brock. During those first few years that he was here, he was interested in making wine and made a connection with Donald Zeraldo, trying to source some great wines for wine production, and they came together and decided to open up a winery called Assimilable, and so went forward with that venture in 1975. Of course, since that period of time, Karl has had such an impact on the Canadian wine industry. He was part of the establishment of VQA. He served on the Canadian Technical Committee for VQA. Certainly we all know him for his important contributions for ice wine production, but Karl is also very fond of Pinot Noir wine, and I'd say his new favorite is probably Sauvignon Blanc, that he also does very well, making it just in his garage now. Such a treat to try that. So through the years, he's had additional connections to us here at Brock. He got his honorary Doctor of Law degree in 1994, and he was also the first lecturer in our wine chemistry course here in 1998 for our Oenology and Viticulture program. Currently, Karl is a professional affiliate with the Research Institute, and today he's going to talk to us about controlling reductive aromas in wine. So with that, Karl, I'll hand over to you.
Thank you, Debbie. Thank you for inviting me, and I hope,
Yep.
So, reduction in winemaking, let's call it basically hydrogen sulfide or rotten egg smell production in winemaking. It's something what every winemaker in his career comes across, and in many cases doesn't know how to correct it, or it gets worse and becomes mercaptan. So this is a problem which haunts every winemaker, or can haunt every winemaker in the world. And so today we are going through the causes of it, and possibly how you can prevent it and how you can cure it, which we hope we don't have to do that. So there's all kinds of wine defects, and if you read from the CCOVI, the list of defects, or from the LCBO, you find different tables, but it always amounts to that the wine can be vinegary, acetaldehyde, leafy, atyl acetate, butyric, and so on. Those are pretty much all those defects are caused by a microorganism. Oxidation, not necessarily, but in most cases, microbes are involved in deteriorating wine, and then of course, if you can have processing problems, that you have filter pad and so on, or cork, the wine is corked, or it tastes corky. And then hydrogen sulfide, rotten egg smell, and then mercaptan, rubber smell, and garlic smell. So what does cause it? Basically, hydrogen sulfide is the reduction, or is the reducted element, molecule from element of sulfur. But how it evolves, we'll go through that. Oxidation is the process in which an atom loses electrons and undergoes an algebraic increase in oxidation number. That's from a book, the definition. Reduction is the opposite. But however, when there is an oxidation in two molecules, if they react to, one is oxidized always and one is reduced. So a simple thing, when sulfur, elemental sulfur, is, let's say, what you possibly could carry over from the vineyard because of sulfur dusting or sulfur sprays, then sulfur can be oxidized to sulfur dioxide, and when sulfur is reduced, it can be reduced to hydrogen sulfide. So the formulas of hydrogen sulfide and water are similar in the molecular structure, the hydrogen sulfide, or rotten egg smell, it's also called sulfur hydride or sulfone. Common other names are, from a winemaking point of view, a rotten egg gas, sewer gas, volcanic gas, sour gas, and stink damp. That's out of the Wikipedia. So, but hydrogen sulfide by itself is very highly toxic, and its toxicity is comparable to hydrogen cyanide. And H2S was responsible, according to one theory, for the great Permian mass extinction about 251 million years ago. But nowadays we find hydrogen sulfide also in a lot of well water, right in the Niagara Peninsula. Many people have to put carbon filters in there, and that's why a lot of well water is not well drinkable. It's also very toxic. The LD50 for hydrogen sulfide in the air is 800 parts per million. Although I've never heard, for example, that a person would die from H2S smell in wine. But the threshold in air is 4.7 microgram per liter, or ppb, and detection level is about 2 for most people. In wine, the flavor threshold is reported as 50 to 80 ppb, and the 20 to 30 ppb according to Dietrich and Staudenmayer. Those are German researchers, and those data I have from symposiums. Today we use 30 to 50 ppb as the benchmark, but the temperature, the pH, the alcohol, and can affect the detection level. In the VQA wines which fail, hydrogen sulfide is one of the most principal components when the tasting panel from the VQA fails a wine. So it is a serious problem, and a relatively high percentage of the wines who fail come from the presence of hydrogen sulfide or mercaptan. It has a very low melting point at minus 85 Celsius. The boiling point is minus 60, so it's basically in a normal atmospheric temperature, it's always volatile. Mercaptan, this is the next step. If hydrogen sulfide is not removed in the wine, it stays in contact from the wine, and it stays in contact with the wine, then there is a good chance it will react with the acetaldehyde in case the aldehydes have not been bound off with sulfiding yet, and or with the alcohol. Now, mercaptan is already much harder to remove. It has It has a boiling point of 35 degrees Celsius, so we'll come to that. So if you aerate a wine, if you splash a wine with a bit of H2S, in many cases you possibly can help to get rid of it through aeration. And we'll come to the three things which take place. But mercaptan is much more difficult to remove. So, and here the mercaptan wine is very persistent and hard to get rid of because of the higher boiling point. Sensory threshold in wine is 0.02 to 2 ppb. In 2000, the Guinness Book of World Records lists A10-diol, which is the mercaptan, as the smelliest substance in existence, and it's pretty nasty. This is something I gave up this presentation at the Fruit Growers Convention, similarly, like in a similar form a year ago, but I added something, and this was something very important. Hydrogen sulfide in a new wine with malolactic fermentation and prolonged lees contact is intended, and the wine will not be sulfited for a long time until the malolactic is over. That means there's all kinds of free aldehydes floating around in the wine. Will likely, if there's hydrogen sulfide in that wine carried over from the primary fermentation, will likely to react with ethanol or with ethyl acetate to form ethyl mercaptan. So wines which are kept unsulfated in the barrel, let's say, and you wait for malolactic fermentation, and you had a carryover of hydrogen sulfide from the original fermentation, this is where you really should watch out for. Now, the mercaptan can become even more horrible. That means if two of those molecules react together, then you have diethyl disulfide, which is ethyl mercaptan. No, sorry, diethyl. And this is a compound which I could not find anywhere the melting point, but the boiling point is plus 154 degrees Celsius. So you would have to boil that wine in a pressure vessel to get rid of that. It's almost impossible to remove. So the historical measures to avoid it, or elimination in wine, were during the winemaking, you make sure to avoid it, and we'll come to that then in a few minutes. A common procedure was that people would put on a late copper spray on the grapes, because copper will react with hydrogen sulfide to give copper sulfide and precipitates it out. Copper sulfate was also sometimes used to dry up botrytis. So, but the danger is, of course, if you have too much copper in the grapes, that you might carry over too high a level into the wine. Or, as in Australia, I don't know if they still do it, but it was common practice that they would add copper sulfate, a blue stone basically, to the juice or the fermenting wine. A common procedure which happened in Europe all the time for maybe 100, I don't know how many 100 years for sure, maybe not hundreds of years, but to use copper alloys on the fittings in the cellar. Bronze or brass, but brass seems to be better because on bronze sometimes, bronze is copper and tin, but I was reading on brass, which is the more shiny element, which is an ally between copper and zinc, but they used to add sometimes lead to that. And there was a winery in southwestern Ontario, and I can't tell you the name, but he came to me because the LCBO failed his ice wine over and over again because he had way too much of lead in his wine. And so eventually I said, asked him what machinery he has, and he said he had an Italian piston pump which was made out of brass or bronze. So I asked him eventually to scrape off with the knife a few shavings and submit it to the LCBO. And that brass housing where the pistons were going up and down was probably had lead in it, and he could not pass the federal government forbids it with more than, I think it's 20.2 milligram, I believe. It's very low for lead. You can see it on the BQA forms. So then sometimes copper tubings were installed, so the wine would pick up a little bit of copper, the same as people would use copper spray, so that the copper would react with hydrogen sulfide and get rid of hydrogen sulfide. However, there are some strategies how you can possibly eliminate it. So once you have it, aeration is an old procedure until maybe 50 years ago when they had, or 60, when they had those big bills on the Mosel and everywhere in Europe with 2,000 liters and 4,000 or 5,000 liters. When they would rack the wine the first time, they would always pump the wine over the top, never push it in from the bottom. And one of the reasons was that the wine would be aerated. And so sulfiding can help, and I'll show you the formula, how the reactions are. Copper sulfate fining and blue fining, well, we want to avoid that. Copper citrate and silver chloride. But here it is. Aeration is the simplest way sometimes is to aerate, since hydrogen sulfide has a low boiling point of minus 61 degrees Celsius, and here's the reaction. This is also important. During the fermentation, if there is copper from the vineyard or from wherever, copper is normally reduced to copper to cuprous to copper plus 1. So in a newly fermented wine, all the copper is present in copper plus 1, not in copper plus 2. So you want to oxidize it through the reaction, to the aeration, which we have. I don't know if we have the formula here. Yeah, no. So copper plus 2 will react with hydrogen sulfide, copper plus 1 won't. So through the aeration, you will oxidize copper plus 1 to copper plus 2. Sulfiding will eliminate H2S, and the formula is here. So in most cases, the aeration and the combination with sulfiding gives the best results. And sulfiding also protects the wine from oxygen, causing other oxidation problem. And what normally happened was that they would normally always pump over to the top of the barrel so the wine would get aerated. And then they would sulfide after in the barrel by mixing it and pumping it over. Not that you add the sulfide into the bottom of the barrel and then you push the wine in through the bottom. You'd neither have aeration and you couldn't have either the reaction that the copper would be oxidized to copper plus 2. Copper sulfate addition, copper will react with hydrogen sulfide and slowly with mercaptans, but that takes time. But copper will not react with diethyl disulfide. And also, this is from my own personal experience, if you add ever copper sulfate, and we come to that, if there's H2S problem and you add copper in small amounts, the wine has to be clean. You can't, it should be filtered if you do it out in the lab, because otherwise if there's yeast particles, it's not likely that you have the reaction proceeding. However, when copper sulfate is needed in excess of 2 to 3 milligram per liter, and copper sulfate is 25% in copper. So if you add 2 milligrams of copper sulfate per liter, you will get 0.5 milligram of copper. But if you're in excess of 1 milligram, then you would have to blue fine. And I'll come to that. And I don't know how many people here do know what blue fining is. I'm sure some of the people who studied in Europe, where blue fining used to be very common, they will know. But yes?
I'm old enough.
Pardon me?
I'm old enough.
Okay. So blue fining is potassium hexaferrocyanide. Actually, that should say here potassium hexaferrocyanide. That's the proper word. So there are now several things to eliminate hydrogen sulfide. Here's the reaction with copper. But again, when copper is needed in excess of 2 to 3 milligram, oh, is that the old? No, here's the formula, potassium hexaferrocyanide. It's called yellow prussate. And copper sulfate and potassium ferrocyanide will not work with diethyl disulfide. So if you don't want to have H2S, you try to avoid that. You have to deal with that by the other problem is you have excess copper, because you add copper to eliminate the hydrogen sulfide or mercaptan, and then you got to add potassium hexaferrocyanide to remove the copper. And that's a very tedious process. You have to be very precise that no cyanide stays in the wine. It is legal in Canada. You can look it up in the Food and Drug Act. But you just should hope that you don't have to do it. So, oh, sorry. What happened, Debbie? Okay, so also, the blue fining nowadays can be also tricky, because virtually most people have stainless steel. From the stemmer crusher to the presses, to the pipe, to the fittings, to the pipes. So it's not likely that you're going to get hardly any iron into the wine. And the LCBO, I think the new forms, they don't even show iron anymore on how much. But in olden days, it was enough iron, because a lot of cast iron pumps were around, a lot of cast iron equipment. But nowadays, iron is very little in wine because of the equipment we are using, which is basically stainless steel. So if there's no iron in the wine, or very little, then you also have a problem even with your blue fining. Then you also have to combine it that you get flocculation, because blue fining is a very fine and light precipitate, and it doesn't come down by itself. So you would have to use silica gel combined with gelatin fining. And you have to be sure that no cyanide is left in the wine. Then you have to test with the Hubach test, which is available from California. And I remember when we had hydrogen sulfide in the wine in the late 70s, early 80s, we had the wrong yeast, and other reason will come to that. We had to blue fine 50% of our wine, and then you have to go to the Hubach test. You have to do that. You have to make sure there's absolutely no toxins in the wine. So copper citrate is a newer compound. where the copper is chelated or held like in claws by the citric acid. And if you add the copper, it's not legal in Canada yet, I don't think so, but it's pretty much legal in many, many countries. And it has the advantage that the copper is fixed to the complex, to the chelate, and it doesn't dissolve all into the wine. So the wine treatment agent for if you have rotten egg smell, copper sulfate, you have the formula here, copper citrate, which is not legal here, but it's legal in Australia and New Zealand and Austria and all East Bloc countries and so on. And the product is called Kupzit, that's from a German company, that's a brand name, and it's basically the copper citrate is bound to bentonite. Silver chloride was allowed in Europe. It works dead on, but it's a heavy metal, so now it's outlawed everywhere. The Swiss were the last ones to forbid it. And it worked beautifully. One of the products were called Sulfidex. It worked both on hydrogen sulfide and mercaptans, even on diethyl sulfide. And sometimes the silver chloride was bound to the filter pads with the diatomaceous earth. So you push the wine through when you were filtering and eliminated your H2S and mercaptan right away. But this is all gone. You can't use it, so we shouldn't talk about it. But so here's just a summary on the impact on a wine. If you use copper sulfate, you increase the copper content in wine, and you have to be careful. The federal law now used to be 2 milligram in copper, but the LCBO had for years 1 milligram as a maximum. 2 milligram was taken from the World Health Organization because the WHO has, I think it's on the next slide, has 2 milligram as the maximum limit for drinking water of copper. And the Environmental Protection Agency in the United States has 1.3 milligram. So, but pretty much every country for wine has now 1 milligram in copper. So if you add copper sulfate, you can increase the copper content. It has a bit of flavor. It can cause possible cloudiness. This is called a casse. It's a French word. It's clouding. And you possibly have to blue fine. Silver chloride increased the silver, bit of flavor, but anyway, it's no longer, we shouldn't discuss it because it's no longer permitted anywhere. Copper citrate is legalized in many countries, but it has one advantage. If you do need it, it has a low increase of copper content, lower probability that you would have to blue fine, and can easily be filtered out because it's bound to bentonite. Now we come to the real thing. What is the cause of hydrogen sulfide reduction or reduction of wine? And here we come to a very important subject, the relationship to nitrogen. And the first thing I heard about that, not with respect to hydrogen sulfide, but the importance of nitrogen for the yeast was in 1991 when I went to the Nitrogen Symposium in Seattle, and it was the whole symposium for 3 days was about the importance of nitrogen in winemaking. There's a link between the low nitrogen values in juice and hydrogen sulfide production during fermentation. During fermentation, yeast metabolizes nitrogen. It needs nitrogen badly. And the needed nitrogen has to come from the medium, that means from the grape juice, or from the grapes original over the grape juice. And it is present in the form of ammonia, but only small amounts. Grape juice does have ammonia. And it's present in a bound form in the amino acid, and there's about 20 amino acids. This nitrogen from ammonia and amino acids can be analyzed for, like CCOVI can do that, has done a lot of work on that, and is expressed as ammonia nitrogen in milligrams of nitrogen per liter, and free amino nitrogen is called FAN in the literature. The sum of both expressed together is called YANC. It's the yeast assimilable nitrogen concentration. So which again is composed of the free ammonia and the amino acid nitrogen. We should remember that the FAN is not as easy for the yeast to extract and use. The yeast has to work hard to pry off the nitrogen from the amino acid. Whereas I call it the ammonia nitrogen is very easily metabolized by the yeast. It's like a candy for the yeast, and the yeast prefers it since it can be immediately taken up and used. The yeast needs nitrogen for the biosynthesis of its cell mass and to perform other numerous biosynthetic reactions. There are about 20 amino acids. Arginine, proline, and glutamine are the most abundant amino acids in grape juice for most varieties and vintages. But we'll see from slides, it differs from year to year. Proline and lysine are virtually not used by the yeast, although it can be quite abundant, proline particularly, but it's not used by the yeast as a nitrogen source. And here I can show you how the concentration of free amino acid changes during the ripening period. Let's say from 9th of August to 23rd of August, and this is from the Nitrogen Symposium 91. Spanholz is a professor in Geisenheim in Germany, and he gave that presentation, and it's so they followed on the Riesling the changes in the amino acids during the ripening stages. So you can see it increases towards the end of ripening, but not every amino acid to the same degree. And the circle, the red thing in circle, is glutamine and proline are not easily used at all, although it's abundant. And arginine is sort of, what do you call it? Most preferred nitrogen sources from the stuff which is present in form in the grape juice is ammonia, but there's not very much of ammonia in grape juice. Glutamic acid is not so abundant in grape juice, but is a preferred source. Glutamine is quite abundant in juice and is a preferred source. Arginine is very abundant. The yeast will also be readily use it, but it's not a real preferred amino acid. But because there's lots of it, so the yeast will use some. Excess of arginine in grape juice over 1,000 milligrams per liter is not desirable, since it can, this is another fact, since it can release urea. And if you recall, when was it, in the 80s, when the LCBO said, when the big wineries who were making sherry and baking it and adding tons of urea, urea is yeast nutrients, and they produced a lot of ethyl carbamate. And the Ontario Minister of Consumer Affairs at that time, Monte Quinta, said to the people on television, don't drink Ontario wine. And the industry was put on its knees. Like, it was a horrible situation for 2-3 years. And part of that was because the wines had a lot of ethyl carbamate, but the reason at that time was not because of arginine. It was because the grape juice was stretched so much with water and then sugar added, and in order to facilitate fermentation, they added tons of yeast nutrients, which was urea. And then shortly after, about the same time, the whole world outlawed urea as a yeast nutrient, and because it's a precursor for ethyl carbamate. And today the federal limit, sorry, what did I do now? No. The federal limit of ethyl carbamate is 30 parts per billion, but the LCB only allows 20 pp at the time of bottling. So, but since the urea is outlawed for now, for a long time, for 20 years almost, ethyl carbamate, I listened to a talk by George Saleas not too long ago, I forget where it was. It's not a real problem anymore. Like, there are no elevated levels to worry about for ethyl carbamate. But you can see here, this is also from Spanholz in Geisenheim, how subtly the ethyl carbamate, which is a carcinogen, changed from the year after 79 to 80. Now, the whole article did not explain, I read it over and over again, why suddenly the drop from about 20 ppb of ethyl carbamate to typical 3 to 5 in that year, and from then on it stayed low. One of the reasons could be that was the year in Europe they outlawed urea. Or a second reason could be, which also was outlawed, that you cannot use wine from the lees and blend it in the wine, because there's a higher portion of ethyl carbamate in the wine from the lees. But anyway, you saw what a dramatic drop in ethyl carbamate happened. Now, this is typical that you might be interested here. There's grape juice nitrogen in Niagara must. And this is the data from CCOVI here, from Debbie, and that's in Vidal ice wine juice, and how it changes from year to year, how the nitrogen available to the yeast, which is the YANC, changes. In a dry year is little, in a weather year is a lot more. That's very substantial. Look at those numbers here on Chardonnay, for example, which we circled. Although we all know that the rainiest years are not the best years for making the best wine. The Burgundy people will tell you that the finest wines are always made in the years with the least rain. And however, there is a big discrepancy in the yeast nutrients available in the juice from a dry year to a wet year. Then this is New York. I have those data from Dr. Henning Klink, a long time ago actually. This was also in that symposium, but for example, the first time I learned about the Niagara juices in New York were very low in nitrogen. When he visited me at Enniskillen, and as I say to you, we had lots of hydrogen sulfide. And one of the reasons was we used the old Montrachet strain Davis strain from Montrachet yeast, which is a high nitrogen using yeast. So the yeast ran always out of nitrogen, and we got H2S. And anyway, we had in our Gamay every year hydrogen sulfide, and he told me that time we were tasting in our cellar, we tasted the Pinot Noir, and Thomas Henning Kling is now in Australia with the Australian Wine and Research. Is he still there? He would. Okay, where is he now?
He's in Washington.
Where?
Washington.
Back in Washington? Okay. Oh, no, he was from Geneva, New York, right. Also, he's back to Washington. Yeah, his wife is from Washington, I think, yeah. Anyway, but he told me that the reason you have H2S in your wines is because all our red grapes here are lack of nitrogen. And one of the reasons, and I'll come to that, Okay, amino acids must before and after botrytis. That's another thing. If you have botrytis in your vineyard, the botrytis mold will use up a lot of the nitrogen which would be otherwise available for the yeast. The influence of nitrogen fertilization on amino acid composition in grapes. It's a very important factor. If you under-fertilize, I know the people who are organic growers, they probably don't want to hear that. But there was a big dilemma in Germany for a long time when people went to under-fertilizing their vineyards. And the vines had very weird aromas, and we come to that. And H2S production was high. So it tells you this is nitrogen per plant. And that was done on potted plants, so they could say exactly how much nitrogen, how the amino acid composition would change. So this is important for the viticulture, is that he has the right, that he knows the right amount of nitrogen what to add to the vines. The yeast and the sulfur metabolism. Both organic and inorganic sulfur compounds are present in grapes, and grape juice, and can be utilized by the yeast. Inorganic sulfur in grapes come from sulfate, sulfite, from the addition of SO2, elemental sulfur from spraying. For grapes in Ontario, you know it's 21 days. If you want to spray with sulfur, it's 21 days for wine grapes. And I think it's only a few days for table grapes. Organic sulfur in grapes include predominantly sulfur-containing amino acids, cysteine and methionine. Now this is where we come to the real issue, the factors which will be affecting your hydrogen sulfide formation in your fermenting medium. The amino acids will play a role, other sulfur-containing compounds, inorganic forms like sulfate in the vineyard, sulfur dioxide, possibly added before fermentation to the juice, elemental sulfur from the spray formulations, from sulfur candles, which means when they were burning the sulfur wicks in the barrels, if the people did sulfur, the yeast strain, I mentioned that before. Some yeast are high nitrogen users, some yeast are lower nitrogen users. Juice composition, how much is in the juice, and the metal containing material, copper, zinc, manganese, and fungicide. Those are all things which influence the around the yeast when the yeast is fermenting juice. During fermentation, sulfur compounds can be reduced to hydrogen sulfide, but it's called Sulfate Reduction Sequence. And those were basically two people from Australia, from the Australian Wine and Research Institute, Henschke and Chironek, who published the first thing. And one of them, Henschke, saw talking about the first time in Stuttgart at interviews when he brought this forward. And most German winemakers weren't very thrilled with it, that the hydrogen sulfide would come from the sulfate. So this now important is, the yeast, when it builds its cell mass, needs a lot of amino acids for that. And two of them, cysteine and cysteine, need basically nitrogen that those amino acids can be formed, which are incorporated into the yeast, metabolized into the building block. So the yeast will turn on, and we'll come to the next thing here. Here it is. This is called the sulfate reduction sequence, the path to make sulfur amino acids, and there's 2 of them. And here, this one here, that's cysteine. Oh, sorry, why did, oh. You can't touch this on the side here. You see, it needs 3 building blocks to form this amino acid, cysteine. Here's the nitrogen. It needs a nitrogen. It needs the organocarbon oxygen thing, and it needs the ACH group. And if the nitrogen is missing, that molecule cannot be formed. So then the yeast will turn on the sulfate reduction sequence. The SO4 can, outside this means this is the cell membrane or cell wall from the yeast. So the SO4 can come from the environment, the SO2. Then here is the pathway. It reduces it to the sulfite, and eventually will reduce to the hydrogen sulfide. And if this hydrogen sulfide, which is produced and turned on, doesn't have the nitrogen available, does not have the nitrogen precursors available, ammonia or some amino nitrogen, it will transport the hydrogen sulfide from the yeast cell inside into the wine medium, and you got hydrogen sulfide. It's basically nitrogen deficiency in the medium, let's call it wine or the fermenting wine, which causes hydrogen sulfide. Because if the nitrogen is not there, it cannot form cysteine and methionine, which it needs for its protein structure. The nitrogen is the second most important nutrient for the yeast biosynthesis after carbon. The great majority of the nitrogen comes from the degradation of amino acids. 60 to 90% comes from only 8 amino acids. That's 69 from Cleaver from Davis University. This is called the fan of free amino nitrogen. Ammonia is preferred, but is less abundant in grape juice. The YANC, as I said, is called the yeast of similar nitrogen content. Not all grape varieties have the same YANC content. Varieties and by location. The weather season, the rainy versus dry, I showed you that slide, and in particular has a large impact on YANC. Previous table from that showed in a dry year and so on, for example, Chardonnay, only 55 milligram of nitrogen per liter in 2007, and those data are from CCOVI here, and 325 milligram per liter of nitrogen in 2008. Here's that slide again. It's basically the slide again to show you how it varies according to the season. And of course, vineyard fertilization too, but the season, here it is. Vineyard fertilization will also influence the fan YANC in the juice, both in terms of total abundance and in composition. Remember the trouble when a lot of wines had defects because of nitrogen starvation in the vineyards. And that's what the Germans had. The English word for it is called atypical aging, and in the German word for it is untypische Alterserscheinungen. That means untypical signs of aging in the wine. They got nasty aromas and so on. In California, the accepted level of nitrogen, pure nitrogen application per hectare is between 50 and 90 kilogram per hectare. I believe the most accepted value is between 60 to 70 in the peninsula, but you can correct me on that. The cropping levels in the vineyard has a significant influence on the fan YANC content. And that's one of the reasons why all our Gamay had hydrogen sulfide because people were under Gamma is a huge producer of it. And they were cropping 7-8 tons an acre. And the grapes had nitrogen deficiency, which I didn't know at that time. It's also important that the nitrogen is very important, and that's on another seminar I attended by Rapp and Versini. Versini is from the University of Udine. That the ester formation, the aromatic intensity of a wine is very important on the abundance of nitrogen. A wine starved, or the yeast starved of nitrogen, will not produce as much esters. Varietal character will be less. And that's one of the reasons also that a lot of those organic wines at the beginning, I think we're right on time. Well, the shortage of YANC, there's low ester formation, and there will be lack of varietal. And here in English it's called ATA when the wine ages, atypical aging, or in German untypical, untypisch aging. This is what maybe some winemakers have do, that they find the juice with bentonite before, or ferment with bentonite. And that's one thing that you should be very aware of. The bentonite finding at typically 100 grams per hectoliter, or 1 gram per liter, will remove up to 30% of the amino acids. It won't remove the ammonia from the juice, but the bentonite will attract or will react with some of the amino acids, or the proteins and amino acids. And this consequently lowers the fan, which may result in a shortage of YANC. So if you have the habit of fermenting with bentonite, you got to be aware, or finding the wine before fermentation with bentonite, you got to be aware, and you must replenish the grape juice with the addition of nitrogen, what you add. So the minimum required YANC is to support yeast during fermentation, is accepted by researchers. In mild solution is 150 grams of 150 mg of nitrogen per liter. But this also varies with the yeast strain. I'm sure that the Montrachet strain from Davies was a lot more nitrogen hungry. Okay. The preferred concentration of all the available nitrogen to the yeast is about 300 milligram of nitrogen per liter. From all the, I don't know if we had it on this slide, one thing we have found that in ice wine juice seldom has a nitrogen deficiency, because when you concentrate from 20 bricks to 40 bricks, two things are normally totally recovered in the ice wine. That's malic acid. There's no loss of malic acid virtually, and there's no loss of the YANC. But this is from all the data we have. I still always use diammonium phosphate for ice wine too. But most ice wine juices have between 400 and 500, between 350 and 500 milligram per liter of YANC. But most grape juices from normal harvest do not have nowadays this amount of YANC. You have to understand, in the vineyard we have very high producing clones nowadays. It isn't like 100 years ago where each plant produced a quarter kilogram of grapes. Because those vineyards, the vines were small, the production was very small. But now You know, you can produce on a Cabernet Franc, you could produce 8 tons an acre, even with only 1,200 vines per acre. So the hydrogen sulfide production is as a consequence of YANC shortage. If there is insufficient nitrogen in the grape juice, the yeast turns on the sulfate reduction sequence to make it in order to make cysteine and methionine. The sulfur reduction sequence pattern makes hydrogen sulfide from sulfate. I showed that before. In order for the yeast to scavenge hydrogen sulfide and incorporate into cysteine and methionine, the yeast needs plenty of nitrogen. I showed it on the molecule, why it is so important. If there is not enough organic nitrogen, the yeast released the hydrogen sulfide into the wine. We went through that before. And here this is a very interesting thing. This is from the Australian Wine Research Institute here. I always touch this on the... Okay. And what you can see here, the yeast runs out of nitrogen, and you have immediate hydrogen sulfide production. When the nitrogen is gone, when the yeast, then he adds ammonia, and suddenly the H2S disappears. So, for example, if you would have hydrogen in your wine, fermenting wine on the 3rd or 4th day, and you would add diammonium phosphate, then within a few hours the H2S will be gone. But that's not a very good procedure, because after 7 or 8% alcohols, let's say 6 or 7, it is not advisable at that time to add diammonium phosphate as a yeast nutrient, because the yeast at that alcohol level stops to be able to metabolize it. Because there's really no more biomass growth of the yeast. And here, this is the sulfate reduction sequence. If low nitrogen, sulfate can form H2S. It's basically the same thing as the other sequence. And here inside the cell you have cysteine and methionine, and here it will produce H2S. And again, it comes from the exterior to the yeast cell. This is like a yeast cell here, from the sulfate being reduced to sulfide, and then eventually reduced to hydrogen sulfide, and it's exported into the wine. If there's nitrogen in there, it will be incorporated in cysteine and methionine. And here again, when the nitrogen is limiting, it's basically the same similar graph. Hydrogen sulfide, let's say you sulfide here. First there's a big amount of ammonia present, and then you sulfide here so that the sulfur becomes available, and hydrogen sulfide development. Those are in model fermentation in the lab at the Australian Wine Research Institute. Diammonium phosphate, the miracle compound to avoid H2S in wine. Okay, I better hurry up. Yeah. Diammonium phosphate, DAP, is a plant fertilizer as well as yeast nutrient. It's 20% in nitrogen, so 1 gram per liter of diammonium phosphate will give you 200 milligram per liter of nitrogen, ammonia nitrogen. In the United States, it's limited to 1 gram per liter of DAP in the BATF rules. In Canada, it says GMP, good manufacturing practice. We actually don't have a limit, as long as you make sure you don't add it at 9% alcohol, because then it'll stay in the wine, and you don't want to drink wine with DAP in it. Okay, So that will supplement the missing YANC needed to avoid. Again, this is the same thing, but just it needs the nitrogen in order to scavenge the thing. If there is a shortage of nitrogen to achieve the biosynthesis of cysteine and methionine, then H2S will be released from the yeast into the wine, and the wine becomes reduced. That's why it's called wine reduction, because it's the reduced form of sulfur. Even if there is already H2S in the wine, in the early stage of fermentation to nitrogen, the addition of that will eliminate the H2S within a few hours from the wine. But again, you got to watch the alcohol, how much alcohol you can add now. If you add your DAP in 2 stages, that's about half of whatever you calculate you want to add. But like I say, typically adding 1 gram per liter of DAP gives you 200 milligram of nitrogen, plus the nitrogen you have from the grape juice naturally is another 150, maybe 120, 180, but we are normally shorter here. Give you about 300 total. You can add it in 2 stages, at the beginning and then after 5 or 6% alcohol, 5 or 6, or in a single stage. That's what you would do in barrel fermentation, because you don't want to go from barrel to barrel and stir in the second dosage. And here again, it's when there is lack of nitrogen, the reduction sequence is turned on. That means you get hydrogen sulfide. Practical consideration to cure minor reductive wine aromas with CuSO4, copper sulfate. Maturated fertile law for copper in wine is 1 parts per million or 1 milligram per liter. The LCBO limit was always 1 milligram, so it's the same. And I brought the one thing with the drinking water already. The danger is also of copper cast. And the copper cast is a clouding of the wine between that the copper is reduced to copper plus 1 to cuprose, and reacts with the protein if the wine is not totally protein stable. And you get a clouding in the wine. This is called copper cast. You can look it up on the internet, and I'll tell you. The Wikipedia will tell you. But so sometimes a small amount of copper added can cure it. It reacts, copper reacts. Checking for H2S macaptan wine, any wine checked correctly for reduced aromas. What is this? If you want to smell the wine in the lab, if you have hydrogen sulfide, if you think you have, always filter the wine. You cannot really test a wine organoleptically if there is yeast colloids in the wine, so you have to filter the wine. Make sure the wine is clean. There's a simple penny test, and most people, you don't have to put your hand up, but I'm sure that most people know the penny test. That you take a wine glass with about 100 milliliters of wine, of clean wine, and have 1 glass which you don't add copper pennies, and the other you do. And if there's hydrogen sulfide left in there, you'll see very quickly how those 2 wines compare, how the copper pennies clear up. This was a learning experience for me too. The copper pennies are not copper anymore. They are, in the US, they are only 5% or 97.5% zinc, but there's enough copper outside because the copper is plated on it. And the same, you can use Canadian pennies. Today they are 94% are made of steel, but 5% nickel and 4% copper plating. So there's enough copper on pennies, and it goes very quickly. You make 2 glasses, clean wine, filtered wine. And there's a simple test that you can be sure you have no hydrogen sulfide. If mercaptan is present, you have to wait longer because it takes a while to pull the H2S off of the ethanol molecule. And then you can do a test with a standard copper solution, that you make yourself a solution and you work quantitatively with an eyedropper or with even a burette with a pipette. And here is a thing, you don't have to write that down that quickly, but you can make yourself a standard copper solution for your lab, copper sulfate solution. And typically, if you have an eyedropper, 1 milliliter of liquid corresponds to 20 drops. Here that would be a table. That 1 drop will give you so much copper, and then you can go by, but you would not go on your test. You maybe would take 4 glasses or 500 milliliters, as long as you are stoichiometric, as long as you're correct volume, like with the concentration. Like 4 drops, for example, in this would be too much, because you would end up already 1 milligram of copper in your wine. So you would know if 3 drops cleans it up, then you maybe would wait for a while with the 2 drops, because you maybe have 0.25 milligram copper in the wine already from the vineyard or from whatever. So here are some last words. Research has shown that wine produced from clean juices have superior organoleptic properties. And that would means normally with solids of less 0.1%. The institute in close to Neuburg in Vienna, they did all kinds of comparison with the most aromatic, the most preferred wines were made from the cleanest, and centrifugation was not the cleanest. I believe cold settling came out on top, if you give enough time for the grape juice to settle. Then you must ensure that you have enough YANC. If you don't have instruments in the house to measure your YANC or your ammonia available to the yeast, then maybe you could go to CCOVI here. Are you analyzing for that? You will be anyway. That will be one of the services provided. But if you don't do that, then you would say, well, 1 gram per liter of that is pretty much safe. That's what I use on my wines making in the garage at home. Then you should, if you don't know another, so make sure at the beginning of the film the juice is clean. Secondly, that you have to make sure when you add the yeast you have enough nitrogen. And then check for H2S. You can do the simple penny test after wine is finished fermentation. If you want to do a more precise or quantitative, you can make yourself a copper sulfate solution. If you have, or if you suspect you have H2S in your wine. And the cupric citrate is legal in many countries, and I would recommend that some type of group of people from here would initiate to approach the federal government to also legalize cupric citrate in Canada. Actually, the whole documentation from New Zealand is actually on the internet, so you have to copy it and show it to the feds. So those are my last words, and then I think Mark Pister, who works at Inniscarr, an assistant winemaker, he was helping me compiling the nitrogen data in a table, and he also, we went through with the presentation of two, and then Debbie Inglis, who helped me last year from the first presentation for the fruit growers coming with the PowerPoint presentation. I don't have a PowerPoint at home, and I would be not very good at it anyway. So, thank you.
Just a comment, Carl. the brass. Brass is made with about 6% lead in it to reduce the surface tension when they make castings.
Right, okay.
So it's very difficult to avoid lead in brass.
But it's brass, it's
Yeah,
not bronze.
But there are two kinds of bronzes. There's tin bronze, and there's a new one that's now replacing brass in a lot of fittings, and that's manganese bronze.
Okay.
That uses manganese and copper instead of
Okay.
tin.
Yeah. Well, no problem. I got that from the Wikipedia, and they say sometimes in brass, lead can be used. But do you think it's a standard form that there is always lead in there?
Sometimes you actually have leads of lead. So when they do the drilling, you end up with lead exposed actually on the surface that's going to be exposed to the
Right.
water. So that can be a problem.
Well, anyway, that guy was burned with the machine, like with the Mancini pump from Italy. So it was a brass pump. Yeah.